Homogeneous codes for energy-efficient illumination and imaging. We demonstrate a small, portable system made from a CMOS camera, a low-power laser projector, and synchronization circuitry that can be used to probe light transport and recover 3D information. Our system can probe the epipolar-only and non-epipolar components of light transport. Both operations are performed optically and run at video frame rate. Notice how reflections from the ball and mirror appear mostly in the non-epipolar image. We align the projector and camera so they are rectified. The projector's laser raster scans across the scene. For a projector scan line, we expose only the corresponding row of camera pixels. We synchronize the camera's rolling shutter so that it moves in lockstep with the active scan line. This scheme blocks non-epipolar light, while allowing light paths along the epipolar plane to reach the sensor. Non-epipolar probing is implemented by inverting the epipolar-only masks. All pixels are exposed except the row corresponding to the projector scan line. The unexposed camera row moves in lockstep with the active projector scan line. Epipolar probing uses a short exposure for each row so very little ambient light reaches the sensor. Using epipolar probing with structured light allows patterns emitted by a weak source to be detected by the camera in brightly lit scenes. To demonstrate, we project patterns directly onto a 1600 lumen light bulb. Our system is able to image patterns from its 5 lumen projector even on the bulb's surface. Ambient light levels can reach 100 kilolux outdoors. Patterns projected from our 5 lumen light source can be detected by the camera even in bright sunlight. Epipolar probing allows our system to recover 3D reconstructions under difficult conditions where conventional imaging systems would fail. By rotating the projector and camera, we can select light paths returned from a depth plane. Changing the offset between active scan line and exposed camera pixel columns moves the captured depth slice. Here we use depth gating to reconstruct objects immersed in smoke by sweeping a depth plane through the scene. Our system can be used to produce a dual video captured by the camera that appears as if it was imaged from the point of view of the projector. As the projector pans from side to side, the image captured by the stationary camera changes as if it were moving. Our formalism allows us to derive efficient codes for probing operations performed with DMD projectors. The codes we derive for epipolar-only imaging are more accurate than previous methods. Notice how indirect light off the mirror does not appear in our epipolar images. Compared to previous codes for non-epipolar imaging, our technique has no discernible streak artifacts. We can now derive codes to implement new probing operations like long-range indirect and short-range indirect imaging. The reflection of the mirror is split into short and long-range components.